OSPF stands for Open Shortest Path First. Now, OSPF is one of the other protocol which is most commonly used apart from EAGRP. Now, the OSPF stands for Open Shortest Path First and it's a standard protocol. Now, the main reason OSPF more commonly used, it supports unlimited number of hops. There is no limit for the hop counts. That is one of the major advantage or the major benefit we get in case of OSPF, and also it's a standard protocol. Now even EHRP is also a standard protocol now, so that's something not a big advantage, but it's a standard protocol initially. Even it is a standard protocol now. So let us see some of the features of OSPF protocol, and then we'll see some of the basic process of OSPF as well. It's a standard protocol. We call this as a link state protocol because it is going to maintain some link state information of the information. So we'll see more on this link state information in our next sessions when we see some OSPF stages properly. It uses shortest path algorithm and unlimited number of hops, and the metric calculation, it is going to see only the bandwidth. It's going to use 10 to the power of 8 divided by bandwidth. So there's the only cost. That's something what it is going to do. So if you have a bandwidth of, let's say, 1544 kbps, so it's going to subtract 10 to the power of 8 it's going to divide 10 to the power of 8 divided by 1544 kbps. It's going to generate some number. I think somewhere around 64 it will generate, and based on that will be the cost here. Administered distance is 110. It's a classless protocol which will carry the subnet mask information along with updates, which is going to support all your VLSM and CIDR concepts. And OSPF supports only equal cost load balancing. If there are two routes and both the routes are having the same cost, in that case it will do load balancing between both the routes. So both the routes it is going to do load balancing. And then it's going to introduce the concept of areas, which is going to make it a little bit easier to manage. So more on these areas we'll be discussing in detail in our next sections anyway. So let us try to understand some of the basic process of OSPF here. Now the entire OSPF process goes in 7 stages. The entire OSPF process goes in 7 stages. We have something called down stage, initialize stage, two-way stage, extract stage, exchange state, and then loading and full stages. So we'll be seeing on the basic process of how exactly OSPF basic process happens. Now the first stage is down stage, where the router A, let's take an example. The router A is having some IP address of 172.16.5.1 and 5.2, and you have some IP address of 192.168.1.1 here and 192.168.2.1 here, or just take the IP address. So in the down stage, both the routers are completely stages. The router A don't know about router B, and the router B don't know about router A. That's something the first stage of the OSPF process. But once we advertise the interfaces, so once I advertise this interface by using a network command, just like we do in our normal RIP or EHRP protocols, it's going to advertise, or it's going to send a hello message on that particular interface, and it says that I'm 172.16.5.1 and I don't see anyone, and this message is sent on a multicast address 224.0.0.5. Now this 224.0.0.5 is the multicast address where all the OSPF routers are going to listen on this particular address, and they identify the neighbors based on that particular address. So it's going to send a hello message, and once we advertise the other interface also, it's going to reply to the hello message saying its own router ID. Router ID I'll be discussing next, and then it says that I see 172.16.5.1 on this network. Now this is a reply, and the reply comes as a unicast packet. So this is what we call as initialize stage. In the initialize stage, both the routers send and receive the hello messages. The router A sends a hello to router B, and the router B replies to the hello message, and then they come to a two-way stage, that is a third stage of the OSPF process, where they establish the neighbor relationship. Now router A becomes a neighbor of router B, and the router B becomes a neighbor of router A, and they build one table called neighbor table. And to verify this table, we can use show IP OSPF neighbor command. So more on the tables again, we have a separate slide dedicated on that. Now this is the initial process. Now the initial process is by default the routers will be in the down stage, that is the down stage, first stage of the OSPF process, where both the routers are completely strangers. And in the second stage, they send and receive the hello messages, send a hello message and get a reply to the hello messages, and then sending the hello on this multicast address, receiving the hello on the unicast address, and they come to a two-way stage, that is the third stage of the OSPF process, where they establish a neighbor relationship and they build a neighbor table. Now the next stage of the OSPF process, the fourth stage, is the XStart stage. Now before we go to the XStart stage, we need to understand something called router ID, because this stage is completely based on the router ID. So let's try to understand the router ID here. Now router ID is an IP address on the router, the highest IP, or in simple words we can say a router ID is the name of the router. Router ID is simple, it's the name of the router. So normally, let's say I got a router 1 and this router is having multiple interfaces, like you can see there is S0 interface and this is the IP address, and this S1 interface, this IP address, and then H0 interface, this IP address. And I got 3 interfaces, something like this. Now by default, if I'm coming from this side, so this router 1 will be identified with this address, and if I'm coming from this side, this router will be identified with this address, and if I'm coming from this side, this router will be identified as 10.001. Now it depends upon the direction, the name of the router changes by default, but in case of OSPF, so this is something what generally happens in EAGRP. So the router name, when we come from here, this will be the router name. If you come from here, this will be the router name, and if you come from here, this E0 interface IP will be the router name. But in case of OSPF, the routers has to be identified with only one common name, whatever the direction. So whatever the direction you're using, the router must have a unique name assigned. So one common name. So whatever the direction. Now let's see what is the default name it is going to take. So let's say I got these 3 interfaces. From whatever the interface you are coming, it's going to by default take the highest IP of the active physical interface. It's going to take the highest IP of the active physical interface, which means here I got 3 physical interfaces, S0, S1 and E0. Out of these 3, which is the highest? Now this S1 is the highest. Now this will become the router ID. Now this will become the router. Assume that this interface is not there. I'll come back to this interface. This interface is not there, and it's going to take the highest IP of this interface, which means this will be the router ID. So that's a default selection process what particular router is going to do. But in case if there is a logical interface configured, like there is something called loopback interface we can create. We can just go to the interface loopback 0, loopback 1, loopback 2, like that. We can assign some IP address, something like 10.001 or something 192.168.1.1, and then the subnet mask. So these loopback interfaces are just the logical interfaces which will never go down, and they just used for testing purpose, for the basic testing. So in case if there is a loopback interface or the logical interface is configured, then it's going to take the highest IP of the loopback interface. So which means the first preference will be given to manual router ID. I'll come to that. Either you can use the router ID manually, there is one option. There is a command called router OSPF1 and then router ID, something like that. We can either give the manual router ID with some command over there. If I don't give manual router ID, by default it will take the highest IP of the loopback interface. If you have any loopback interface, like in this scenario, I got 3 physical interfaces, 1, 2, 3, and I got 1 loopback interface. So the router ID, it will select the router ID will be selected based on the loopback, and if there is no loopback, if there is no manual, then it will take the highest IP of the physical interface. In most cases, by default, it will take the highest IP of the physical interface, if assuming that there is no loopback and assuming that there is no manual router ID commands. So router ID is a name which has to be unique in the OSPF database, and it is going to identify one router, and whatever the direction, it will be identified with only one common name. So that is what we call as router ID. So understanding the route ID is really important before you go ahead with the extract stage. Like the fourth stage, if you remember what is the fourth stage, we have discussed. Now there are three previous stages what we have discussed: the down stage, initialize stage, and the two-way stage. Now the next stage, the fourth stage, will be extract stage, where they will decide who will start the exchange first. Like this router says, I will start the exchange. My router ID is this, assuming that the router ID of this is the router ID. Now this router says, no, I'm going to start the exchange because my router ID is higher than your router ID. Now in the extract stage, they will not exchange, but they decide to exchange, and they decide to exchange start. So now what generally happens is, they are deciding if router 1 is having the higher router ID, router will send first. If the router 2 is having a router ID, router 2 will send first. So that will be decided in the extract stage, and in the exchange state they do the actual transmission. So they do exchange their own summary of the databases. Like the router 2 will send first because it is having the higher router ID. It sends, here is the summary of my link state database, and then the router 1 also will send information that here is my summary of the database. Now once they send and receive the summary of the databases, now here DBD stands for database description, nothing but database description packets, which is going to carry your information, or it's kind of update. It's kind of update which is sent by the routers. So the next thing, the last two stages, loading and the full stages. Now before we go and discuss or finalize on these 7 stages, we need to understand something called OSPF tables first. And especially in this, we need to understand OSPF database table. So that's something relating to this loading stage. So let's try to understand the tables. Like if you remember, in the EHRP we have discussed the neighbor table, and the neighbor table contains a list of directly connected routers. Like if you have a router 1 connecting to router 2, router 3 and router 4, and if I use show IP OSPF neighbor on the router 1, I can see there are 2 neighbors, that is router 2 and router 4 routers, and you can verify with the neighbor show IP OSPF neighbor command. Neighbor table contains a list of directly connected routers. So who are my neighbors? That information will be propagated, and then also it is a basic verification command which we use. If there is no communication from router 2 to router 1, the first thing we'll see whether they form the neighborship or not. Okay, so same like EHRP, there's no change, and the routing table is also same, which contains the best route, best path to the destination, more like a normal routing table. It's a normal routing table only, but the database table is slightly different when you compare with EHRP. So let's get back to EHRP, what we have discussed. Let's say I got a router A connecting to 3 different routers, router B, router C and router D, and these specific routers are having some information. Like let's say this router knows 5 routes, and this router knows 3 routes, this router knows 2 routes to reach some destination. Let's say there is a destination called 50 network, and to reach that particular 50 network, these particular routers are having some information on how to reach this network. Let's say the router B knows 5 different routes to reach 50 network, and router C knows 3 different routes, and router D knows 2 different routes. Now if you remember, in EHRP we discussed that even though the neighbor knows 5 routes, from each neighbor, EHRP is going to exchange only the best routes. In EHRP, it is going to exchange only the best routes, which means the neighbor will only advertise their best routes. That's it. And the same thing happens here also. The neighbor will exchange only the best routes, and these best routes will be collected and placed in a topology table. That's what we discussed in our previous sessions in EHRP. So the difference between your EHRP topology table and database table is, now in this scenario here, like when this router is sending, the neighbor has to exchange all the 5 routes, and here also the neighbor has to exchange all the 3 possible routes, and this neighbor has to exchange all the 2 possible routes, and all this is going to maintain in the OSPF database table. Now the OSPF database table is going to maintain all this information, and it's going to maintain each and every possible route. Now in OSPF there is a condition that every router must have the same database table. So all the routers must have the same database. So which means if I know 10 routes, you should know 10 routes. If I know 10 possible routes for one destination, you should have the same information. So all the routers must maintain the same database. That is a condition in case of OSPF. That's the reason the neighbor, they don't exchange the best routes, they will exchange all the possible routes. Okay, so we'll come back to this condition more in detail in our OSPF areas concept, but that's what the default behavior, the behavior difference between the link state and a distance vector protocols. Now distance vector relies on the information which is given by the neighbor, and it's going to build the best route based on the best routes given by the neighbor. But in case of link state, even though it is learning about that particular network from the neighbor like P, C, D, but still it's going to maintain each and every link state information. Link state means how it is connected, how many possible routes, and how many different routes we have. Each and every possible route information it is going to maintain in the OSPF database table. Now the OSPF database table is more like your maps, online Google Maps. If you are going to open, the map remains the same. Whoever opens, it won't be any difference. Like if I want to go to any specific destination, I'll use my map online, and I can just use that particular map to reach any specific destination. So only the difference is from my home, this might be the best route. Maybe from your place, this is the best route. So the best route might be different on each and every router, but what matters is both are going to maintain the same map or the same database. So that's the condition here in case of OSPF. All the routers must have the same database. Now let's get back to our OSPF stages where we have left. Like we have seen the 5 stages. In that the first stage is down stage, initialize stage, two-way stage, where they form the neighbors and build the neighbor table. And then in the extract state, they will decide who will start the exchange first. And in the exchange state, they will exchange their own databases. That's what we call as link state database. And then now coming back to loading stage. When the loading stage, what happens is my router A, let's give some names. The router A is going to check its own database. This is my own database. That's what I have. And already I have received some database information from the neighbor. Now this is the database what I received from the neighbor. That's what you have said in the previous stage. If you remember, the previous stage, what was that? Exchange state. Now my router is going to compare my own database with the neighbor summary database what I received. Summary of the link state database in the previous stage. Now ensuring that both are same, that's something it will check, because if you remember in the previous condition we have seen that OSPF database must be same on all the routers. So both the neighbors will check with each other that we must have the same synchronized database. Now in case if I realize that there is some extra networks or extra information or extra routes I have, what I'm going to do? I'm going to send a request. What I'm going to do? I'm going to send a request. That's what we call as a link state request. And then I'm going to say that I need a complete entry for so and so network. Now the reason is in your database I have seen that you have some extra information or extra networks or extra routes. That is something what I don't have. But whatever you have said in the previous stage, that was just the summary of the database, not complete. So I want that complete information now. And then the router will reply with link state update saying that okay, take this information, here is the complete entry for so and so network. And then I'm going to send thanks for the information, and the same process will happen on the other side also. The same thing happens. The router checks the database, checks the neighbor summary database, ensuring that both are same. And then if it is not same, it's going to send a request and get the update. And then finally it sends an acknowledgement packet saying that thanks for the information. And then they come to the full stage where both the routers have the same synchronized database. and based on that database it's going to calculate the best route based on the formula 10 to the power of 8 divided by bandwidth, and write down that best route in the routing table, and your actual forwarding happens based on the routing table whatever is calculated. Now, understanding these 7 stages is really important for you to know, but when you advertise for the first time, so this process happens in fraction of seconds. But it's a something basic process. You need to understand what are the different 7 stages uh, in OSPF process when you advertise. And the next thing, what is route ready? Route ready is the highest. It's something identified. One router is identified with some a specific name, and it should be unique name and a common name, whatever the direction. And then the tables, like the major difference between the OSPF topology, OSPF database table and EHRP topology table is in EHRP it's going to maintain only the best route information, whereas the database is going to maintain all the possible routes information. That's the major difference between OSPF database table and EHRP topology table.